I made an announcement last night where I actually suspend assignment for now. Okay, no assignment this week, no assignment next week. For those of you who have not seen, the announcement, and of course, I did that for you to be able to have more room to prepare for the midterm too, because I want the minimum in the midterm too to be 100%. So that's why I did that, which is possible. And not only that, I've extended the deadline for submission of the ongoing assignment by 48 hours. Okay, so going to welcome you to principal component analysis. Of course, we've done that before, but I'm going to walk you over some example. How do we do it in now and stuff like that? Okay, so the PCA application in real life are examples. I'm basically starting from two variables here. But let me tell you before I go into the example, based on what I presented the other time, if I want to construct the principal component analysis, I actually going to either work with covariance or correlation matrix. I'm going to say that again. If we want to construct principal component analysis, we can work with covariance, we can work with correlation. Now, there have been a kind of, maybe I'm going to say methodological disputes between covariance and correlation. And of course, in principal component analysis, the debate between covariance and correlation continues. But I'm going to tell you now which one is the most appropriate to use in a given situation. But before I tell you which one is more appropriate to use, I will first tell you what is the meaning of covariance? What is the meaning of correlation? I'm going to say, when I talk about covariance, I'm talking about joint variability between two variables. The joint variability between the two variables actually means that measures how two variables change together. Okay, that is what we call covariance. But if I want to measure how closely two variables are related, okay, how closely two variables are related, then I'm going to be talking about correlation. Okay, now let me tell you this. The fact remains that they got the similarity they got together is that both covariance and correlation actually indicate the direction of the relationship. Okay, but the difference between them is that if we want to put into consideration the magnitude of the relationship, the strength of the relationship, what do I mean by strength? Whether weak, strong, or no correlation at all. So when I want to talk about the strength of the relationship, then correlation matter. So which means if I want to talk about the strength, I can use covariance. But let me tell you this. The fact remains that when I standardize covariance, then I'm actually going to have correlation. Standardizing a covariance will lead to correlation that will introduce a limit. And that very limit will be from -1 to 1. You don't have that limit in covariance. But it's just like, I remember when I was, dating my wife, when we were still boyfriend and girlfriend, maybe 20-something years ago, it means the two of us actually changes together. That's a covariance. You now get to a point that I said, can we take this relationship to another level? Taking it to another level is like, oh, can we have a way to standardize this relationship so that there is going to be a limit? Maybe before I don't have a limit, I'm just going from one point together. With that, I'm actually going to have a limit. So that is the way you got a limit for the correlation as well. Okay, now, since you know the difference between the two, I'm sorry, the way I understand my stats, the way I understand my math, I understand by relating to real life, practical situation. Because what happens in real life happens every day. That will enable me to understand. Now, I want to start this example with two variables. Let me tell you, with two variables, there's no issue. But what if in a situation where the two variables correlate? Take a look at these two examples. I'm trying to look at, effect of weight and the percentage body fat for adult males on a particular response. And I want to use these two variables in a model. Of course, percentage of fat could contribute to weight. They may correlate. Because of that, I want to construct a principal component analysis. Okay. But let me tell you, the right approach here is to go for correlation instead of covariance. Why? Because they don't have the same scale. Look at that. I'm talking about the weight. I'm talking about the percentage of body fat. The two of them don't have the same scale. We use correlation when the two to construct principal component analysis when the variables involved, if they do not have the same scale. But you only use covariance when they have the same scale. Does that make sense? Okay. Now, this is a scatter plot of the two variables. Now, I want to, construct a principal component analysis. You get the color means, because we need the mean of the weight, the mean of the body fat, the mean of the two variables. We also need their standard deviation. Okay, you can see that is the R code. We also need the variance or covariance. And as you can see, with the variance covariance, I want to get my PCA. But I told you that when they have a different scale, you should go for correlation. But let me use covariance and let me see what is going to happen. So that is a code, for covariance. As you can see, scale equal to false. Take a look at that. Now, that will generate a result. Oh my God, take a look at what I have now. If you take a look, if you see the first result here is what we call the standard deviations. Do you know that the standard deviation that you are seeing now, when you square that, when you square 21.409819, and when you square 5.982714, those are the variances. I'm actually going to call that agent values. When I square the standard deviation now, they become agent value. The agent values lambda 1 and the lambda 2 that I talked about the other time, the lambda 1 here is 21.409819 squared. The lambda 2 is 5.982714 squared. Of course, the lambda 1 is it is the variance of the first principal component. The lambda 2 will be the variance of the second principal component. Of course, the variance of the first will be bigger than the variance of the second. Now, when you take a look at the rotation now, the rotation is where you have the eigenvector. Now you got principal component 1, principal component 2. Why do I have PC1, PC2? Because I actually have, originally, I got two variables. The numbers of principal components that I'm actually going to produce depend on the numbers of the original explanatory variables. Now we got PC1, PC2. And of course, when you take a look at the PC1 and the PC2, it's basically a linear combination of the old one. You can see the PC1, you're actually going to have a weight for weight, the coefficient for weight, the coefficient for body fat. Okay, you're actually going to see the two in the PC1 and the PC2. Now, when you do the print of the summary, you can actually look at the proportion, the cumulative proportion now is going to tell you the percentage of the contribution of a particular principal component. When you take a look at the PC1, the PC1 contribute 92.7%. If you take a look at what you have, and the PC2, if you look at the proportion of variance, you know, the proportion of variance here is looking like a random effect. If you take a look at what we do in the random effect model, and we're trying to, investigate which random component contribute the most. Well, here now we're trying to say which principal component contribute the most. PC1 now, if you look at the proportion of variance, is 0.9276. If you look at that of the PC2, it's 0.07243. And, the equation from the PC1, PC2 is what you are seeing. But let me tell you, based on the threshold of 80%, at least 80%, I'm basically going to go with the PC1. I will eliminate PC2. I'm not interested in the PC2. Because losing a threshold of at least 80%, the PC1 is already 92.7%. Take a look at that. Okay, now it means if I want to carry out my regression, don't forget, up to this moment, we've not considered the response variable. It is, you only consider the response variable after you have successfully decided on the number of principal components you want to tolerate, because you're actually going to conduct what I call a principal component regression. The principal component regression will now mean, okay, I'm not going to use the original explanatory variable again. I'm only going to use the principal component as the explanatory variable in my regression analysis. Okay, now what am I trying to show? Do you know that from the principal component y1, I can derive the variance of y1? But I told you the variance of y1 is a lambda 1. If you take a look at the force, the standard deviation given 21.409819. When I square all those standard deviation, the first one is going to be the variance of the y1. The second one is going to be the variance of the y2. But if I want to derive that manually from the principal component equation, I can just do variance of y1. Then using the fundamental principle of statistics, do you know that when I plug in, this is going to be in terms of the variance of x1, the variance of x2, the covariance of x1, x2 that I already know from the previous analysis. When I plug that in, that will automatically give me my variance of y1. If I want to derive that manually, I'm also going to do the same for the variance of y2. Okay? Okay, this is what I was trying to explain the other time. If I want to talk about the contribution of a principal component. So the contribution is going to be, okay, the variance of the first principal component divided by the total variance. Oh my God, you do the same in random effect model. The only difference between this and the random effect model, like here you don't have variance of residual. In principal component, there's no variance of residual. But in a random effect model, you have the variance of the random component plus the variance of the residual. That is the total variance that you're basically going to put in the denominator. Take a look at that. So what is the message here? The message is more or less like, I really want to know what is the contribution of the principal component analysis. Take a look at that. Okay. I think I've explained this the other time. Covariance or correlation. We need to use correlation when we realize that the variables under investigations, they don't have the same scale. So which means we need to standardize. The correlation is already a standardized covariance. I'm going to say that again. Correlation is a standardized covariance. When you standardize covariance, you got correlation. Now, you know what I've done before? Using the covariance, I want to use the correlation matrix now for the two variables. That's exactly what I'm doing. Take a look at that. COR, in R. That is what you're going to use to get a correlation. Now, don't forget, how are you going to recognize correlation? The diagonal, the right diagonal of the correlation matrix is going to be 1, 1, 1. Take a look at that. Then construct your principal component analysis based on that. Let me tell you this. If we're working on the same data, I want you to pay attention to what is on the board. You're basically going to see that the standard deviations of the two principal components here will be different from when we make use of the covariance. Take a look at the standard deviations now. 1.30786740, 0.538036. That was not what we got when we use the covariance. Okay, now look at the rotations. I mean, the eigenvalues is different from what we got when we use the covariance. And when you take a look at the proportion of the variance now, the proportion of the variance of PCA1 is 0.8553. I remember the other time it was 0.92 something. At that time, the covariance have not been standardized. So this is going to be preferred in most of the situations. I'm going to say in most of the situations, particularly situations where the unit of your explanatory variables is not the same, or they are not being measured on the same scale. So I would prefer that we go with the correlation matrix when we want to construct the PCA. Okay, so if you take a look at that now, the idea of the principal component analysis is to reduce the dimensionality. When you have more dimensional, when you have high dimensions, situation will look so complicated. I'm going to say that again. When you have high dimension, the situation will look so complicated. And how can we adequately reduce the dimensionality in such a way that we're not going to lose total information? Of course, the majority of the information will still be retained. I gave you an example the other time. Like, I want to take a picture of about 200 people, of course, and I want to capture everybody. I'm just going to be figuring out where am I going to stand to take the picture. I know the photographers face a lot of that issues when they are taking, when they want to take pictures. But I know there's a new technology now, like a drone. Some of them now use drone to, to do that. So the idea behind the principal component analysis is, if I have a multi-dimensional problem, can we have a way to simplify that? Like, that's what we do in mathematics. When you take a look at mathematical problem, there was a time I was solving a math problem. I used like 5 pages. Do you know what I got in the end? I got 1. I was like, what's going on here? So my final answer is just going to be 1. And look at, so which means life present itself in a complicated way. But if we really want to tackle life, we simplify life. That is just it. Okay, that is what we're trying to say here. Just one dimension instead of 2 dimensions. If you take a look at the PCA1, PCA2, the solid line represents the PCA1, and the dotted line represents the PCA2. You can see the line, 2 different lines. But what are we trying to tell the world? If you take a look at these 2 now, of course, we're going to go with the PCA1, as you can see, because with even though there's going to be some loss of information, but we're still going to be fine. Take a look at that. Now I want to take us to so many variables. And I'm going to use an example from sports. I like athletics a lot, track. Oh my God, I love it. There was, how do we, when we have so many variables now, we want to go beyond 2 variables, how do we choose the number of components? Okay, how do we choose the number of principal components? And because of that, I'm actually going to consider an Olympic, the heptathlon. I don't know whether you've watched Olympic, where you basically going to see one person running different kind of race, like they're going to partake in 100-meter hurdle, shot put, high jump. I think that was introduced in 1984 Olympic. And of course, a scoring system is used to assign points to the results from each of the events. And the winner is going to be the woman who accumulate the most points over 2 days. Imagine doing more than one event over 2 days. You do hurdle, you do shot put, the same person doing high jump, 200-meter run, long jump, javelin, 800-meter run. Now the question now is, can we have a way to prune down days? Because this is going to lead to high dimensional problem. And how can we reduce the dimensionality of this particular problem? And another thing is, how many principal components should we select, to get the benefit of the dimensionality reduction? Now, I'm going to start with the data. Like, if you want to have access to the data, you need to install, this data on, heptathlon. You need to install a package called HSAUR. Okay, when you install that package now, you need to load that. Then you're going to have access to the data, what I'm giving you now. This is the first 6 observations in the data frame. There's a lot of them. Take a look at the first person journal. Cassie from the United States participated in hurdle, high jump, shot put, 200-meter run, and so on like that. This is just displaying like 6 persons. There's a lot of them. I just say head. Head means show me the 4, 6. Okay, now we got a lot of variables here, right? And we believe, why are we so worried with a lot of variables? We're so worried because there's basically going to be some that are related. And when explanatory variables are related, when an independent variable are related, they will give the same statistical information. We don't want that kind of situation where 2 explanatory variables give the same statistical information that will lead to problem of multicollinearity in statistical analysis. It's more or less like you having a 2 captured in a ship. They're going to be dragging, they're going to be competing for space. And that's why we're looking for a way, to actually reduce that. But the issue we got while we're using the principal component analysis, we have not decided on the variable to eliminate, maybe based on theoretical theory or based on maybe reviewing the literature. Maybe we realize that all these variables are important, and that's why we don't know the one to drop. We're not interested in variable elimination, but we are interested in variable extraction, feature extraction, and that is why we're using the PCA. Okay, so what am I doing right now? We removed this course since it wasn't one of the, okay, at times you may have, the score is going to be probably the response, right? Probably the response variable. And like I said, we're not interested. Maybe that very score is on column 8. So we're removing it so that we're only going to have explanatory variables only. And when we have explanatory variables only, when you take a look at all those, the scale here are not likely going to be the same. When you look at the scale for all those, for high jump, for short put, and so on like that, and because of that, we're using correlation matrix. Take a look at that. So I'm presenting to you now the correlation matrix. You know, some of you may be wondering, what do we have a round? Round. I'm rounding down to 2 decimal. That's why you see 1.00. And when you see the diagonal of the correlation matrix, you can actually see 1, 1. So I'm presenting to you now the correlation matrix. Now, this is a scatter matrix. You know, for every correlation matrix, you're also going to have a scatter matrix. The idea behind the scatter matrix, you're actually going to have the scatter plot for the pairs of, of the possible pairs in the standing. Now let's consult the principal component analysis now. Because we got how many variables? I think we got 7 variables initially. Let's take a look at that. How many variables? 1, 2, 3, 4, 5, 6, 7, exactly, 7. Don't forget the column 8, score. We're not interested in that. That's a dependent. Okay, if I want to construct a principal component analysis, in fact, that is one of the drawbacks of a principal component analysis. You know, not considering the response variable, focusing only on the explanatory variable. That is one of the disadvantages of the principal component analysis. Okay. Now, because we got 7 original explanatory variables, we constructed 7 principal component, PC1, PC2, up to PC7. If you take a look at the standard deviation, 2.1119, 1.0928, and so on like that, you know that when I square the standard deviation, that will actually be lambda 1 for PC1, lambda 2 for PC2, okay, which represent the variance of the principal component. When you want to look at the cumulative contribution now, because if you really want to know how many principal component am I going to decide upon to be able to, benefit from dimensionality reduction, we got a threshold. Let me tell you this. When you are using correlation matrix for your principal component analysis, we can use a threshold of 1. When you take a look at, the standard deviation, a principal component that have more than 1 value of the standard deviation should be considered. But I cannot use that threshold when I use a covariance. I'm going to say that again. You know, to decide on the number of principal components to choose, when I actually when I construct my PCA through correlation matrix, then I'm basically going to choose the principal component whose standard deviation is more than 1. Okay, but in general, if you work with covariance, that is not going to be a threshold. That's going to be a correct threshold. If you work with covariance, you talk about at least 80%. Talk about in terms of contribution. Cumulatively, we can also use that threshold here for correlation as well. Take a look at that. Let me first use the first threshold. How many principal components actually has a value greater than 1 in terms of standard deviation? You're basically going to see is PC1, PC2, right? If you take a look at that. And if you want to go by the cumulative proportion of PC1 and PC2 contribute 80.78% cumulatively. Don't forget the threshold of 80. So which means I'm basically going to choose PC1 and PC2. You know, the corresponding, we take a look at the rotation now. Those are the eigenvector which you're going to have from PC1 to PC7. Okay, and since I've chosen PC1 and PC2, then I'm only going to choose the rotation that corresponds to PC1 and PC2. The remaining PC7 is here, it's not missing. Okay, so to tell you, you have auto that. Okay, so I say we're going to choose. Now, I want you to take a look at this now. We're choosing PC1 and PC2. I want us to focus now on the PC1 and the PC2 that we have chosen. What is it meaning? I want us to look at the PC1. I want you to look at hurdles, high jump, short put, run 200 meter, long jump, and the run 800 meter, they actually have a huge value, right? Javelin in PC1 is very, very low, right? So which means the PC1, okay, actually is displaying the significance of those events. But when you take a look at the PC2, oh my God, look at the javelin in PC2. So which means the relevance of PC2 is just the javelin. Why the other event? And that was why I came to this conclusion here. I said the first principal component appear to be what it takes to win. It is a combination of the quick time for hurdles, run 200 and run for 800 and high, or long jump distances for that and that. And why the second principal component appears to weigh the importance of javelin. Is that not what you're seeing? I wanted to take a look at that now. PC1, PC2, we're looking at the weight. Don't forget, in each of the principal component, you still have the original explanatory variables, and you can see it in terms of weight. You're actually gonna see the importance of the whole variables. Take a look at that. Of course, we're not using PC3 up to PC6. As far as we're concerned, they have no meaning. Okay, so now, but let me tell you this, the file remain. We are just using 80%. Don't forget the contribution of the PC1 and PC2, which means our effort will also lead to loss of information. Let me tell you this. When we make an attempt to model the world is probabilistic. The world is stochastic. Because of that makes the world to be complex. And if we want to understand the world, we need to simplify the world. When you want to simplify a complex situation, there will be loss of information. No matter how we do, there's always going to be loss of information. And that is the reason why model can never capture exact reality. And that is why in statistical analysis, there's going to be a residual. There's always going to be a place of error. And what we do all the time is to minimize residual, no matter how we try. Error can never be zero. That's what I used to tell my wife. If my wife is angry, I'm going to say, oh my God, don't remember that I'm a human being, right? I will continue to improve. That's what I used to tell my wife. So no matter I continue to improve, I will never reach perfection. There's always going to be a room for error. Okay, that's similar to statistical model. Okay, so I think I've explained the cutoff point that I mentioned, the 80% rule. Okay. Excuse me. So now the next thing I want to talk about is I think I've also talked about this guy. We can also use what you call a plot. Like there's something that we call a screen plot. You know what this guy is trying to tell me? It's just going to give you the contribution of the PC1 and the PC2. Of course, the PC1 is 60 something, that one, the cumulatively, that was what gave us 80%, more than 8%. The reason why we consider the PC1, PC2. If you take a look at the other PCs, they are not that significant. And that's why we're not interested in them. This is another graph, another plot for that, call it screen plot. whichever one you want to go with, the two of them are given the same information. Okay. Okay, so so I said let's transform the data into principal components pay by rotating the data using the da. I think I'm still explaining what I've done before. Let me see. Yeah. Okay. Just explaining what I've done before. Now let me come where, okay, in the data that I was using before, the two variables data, we choose two principal components. Okay, we choose two principal components and let me see. Yeah. Okay, so if I want to make use of the two principal components now, we have for the first data point, if I plug in, I can think of a value, 150, 150,10, like, okay, well, when x1 equal to 150, s2 equal to 10, when I plug that in, that is what I have. So this is like predicting, getting the principal component value from the original value. So making use of the equation. So that is the, the essence of what we're doing here. And of course, yeah, I think I've explained, all of that, the scale one. Okay, so let me just the takeaway from the principal component. Let me tell you this: I'm not a fan of principal components. I'm a statistician that doesn't believe, even though it solves a problem. But let me tell you the issue that I have with principal component: the fact that even though it solves a problem, I appreciate those who actually, initiated this. It's part of the way, to or solve a problem. But the issue I have with the principal component is that the relationship between the variables and the response was not put into consideration. They only focus on the explanatory variables. They leave out the response variable. And let me tell you this: do you know that the unselected principal component, because in the end, we're basically going to use a rule to select few numbers of principal component. There's possibility those ones that you did not select, they may have an important information to the prediction of the response. So which I call one of the drawback of principal component analysis. Well, like I said, it's an alternative. It's a very good, a very good alternative. Then another thing with the principal component analysis, if I select PC1, PC2, if I select a number of principal components, and I conduct a principal component regression, what kind of interpretation do I want to give? When I'm working with the old variables, I'm looking at the effect of, okay, this variable on the response, effect of this. But right now, I'm going to be looking at the effect of the principal components. The interpretation becomes crazy. And that was why I asked a question the other time. If you want to go with the principal component analysis, you need to be, if you are comfortable with less interpretation. Generally speaking, let me tell you this today. We got two intentions in the scientific world. I'm going to start with this. There is basic science. There is applied science. In basic science, we make an attempt to understand the world and explain the world. In applied science, we look at the relationship among variables to predict the world. But I'm going to tell you this. Your understanding of the world does not mean you can predict the world. I'm going to say that again. If you understand the world, okay, you can explain the world. That does not mean you can predict the world. I'm going to give you this example now. The fact that I have a gas in my car does not mean I can predict where the car will go. I'm going to say that again. The fact that I get a gas in my car, okay, that doesn't mean I can predict where the car will go. I'm going to say this again. The fact that I understand how car work, because one of the way car is going to work is to have a gas in the car. The fact that I understand a car does not mean I can predict where the car will go. I may be thinking that the car is going to go to Chicago, and the car eventually go to Philadelphia. The only decision to know, the person who know where the car goes is the driver. So, and that is the reason why explanation is not the same thing as prediction. In statistics, in psychology, in sociology, in economics, in the scientific community in general, we pursue an explanatory goal. We pursue a causal goal. We are interested in explaining, going retrospective to explain what has happened in the past. That is what we do in scientific community. But when I talk about prediction, then that is a major concern of the machine learning world. And let me tell you this. Assumptions in statistics are not assumptions in the machine learning world. Because the intention in the machine learning world is prediction, not to explanation. If I want to make the best prediction, I need a lot of variables. If I want to make the best predictions, I need a lot of variables in my model. And that is why the machine learning world, they actually use what I call, very good with high dimension, with big data. But the problem with the machine learning world? Problem of interpretations. I need few variables in my model to be able to make interpretation. In statistics, we got issue with prediction, even though some statistical model also do prediction. But you cannot compare the statistic, the power of a prediction using statistical model compared to the machine learning world. The power is less. And that is the reason why we need a combination of the two. Statistical knowledge, the machine learning knowledge. You now need to define your intention. Do you want to explain or do you want to predict? But there's an effort in statistics now. Because we believe what is going to be gainful to the scientific community is how we can translate a model that explains to a predictive model. But if we want to do that, we must be ready to relax some assumptions. There's a lot of assumptions in statistics. But the facts remain. Whether you're talking about machine learning, you're talking about whatever, they are all variants of statistics. Because the machine learning uses the fundamental principle of statistics. And that's why I'm going to call myself an hybrid statistician. A statistician who understand machine learning and also understand all the nitty-gritty in statistics. Statistics is more or less like a story that goes on and on and on and on. Is there any question before I go today? Is there any question? So like I said, there's no assignment this week. There's no assignment next week. Just for you to have enough room to prepare for the final, for the midterm too. Make sure you get yourself familiar with the midterm 2 practice questions. Of course, I'm still going to come to this class where I'm going to walk you through some practice questions. But I want, I told you the other time, the fact that you did not score A in midterm 1 does not mean you can score A in midterm 2. And if you score A in the final, of course, you have A in this class. They are going to be very, very easy. So what I just expect from you, you don't understand something, visit me during my office hour. And the ongoing assignment is also extended by 48 hours. You can check the course, the syllabus for that. I think I also pruned down the number of assignments in the semester to 9 now. Yep. I think instead of 10, we now have 9 assignments in the entire semester. You're still dropping 1. I'm still going to drop 1 automatically, the one you have the lowest score. You still have opportunity to have A. Wake up. You can still get, hey, make sure you stay safe and have a lovely day. But for now, everyone,